So we're going to have a look at our exponential function in a little bit more detail and how we differentiate them. Because we've got these functions, obviously we want to know how to perform calculus on them to make them really useful. So let's do it by first principles. If I've got an exponential, so function x will be a to the power of x, function x plus h, a to the power of x plus h. So we sub it in our first principles formula, and this is what we get. Got a problem, because if I sub h into the bottom of the fraction, I'm going to get 0. Sub it into the top of the fraction, I'm going to get 0 as well. So what do I do with this one? What I do is I factorise out the a to the power of x. Now I can bring that to the front of the limit, because h approaches 0, it's going to have no effect on that factor of a to the power of x. So I'm now left with a to the power of h minus 1 over h. So we're going to look at this in a bit more detail. A to the power of h minus 1 over h. I could rewrite that as a to the power of 0 plus h minus a to the power of 0 over h, which I could say is function 0 plus h minus function 0. Well, that's the derivative at x equals 0. So in other words, it will be whatever the slope of the tangent is at x equals 0. So if function x is a to the power of x, then f dash x will always equal some constant m times a to the power of x. And m will be the slope of the tangent of that curve at x equals 0. Whatever the slope is at x equals 0, it'll always be times that number. So let's introduce Euler's number, e. It's another irrational number. It's just like pi, 3.14, etc. Goes on forever, never repeats. The definition for e is this. The limit as n approaches infinity of 1 plus 1 on n all to the power of n. As you plug bigger and bigger numbers into that, you'll get closer and closer to the value of e. Your calculator will give you something like this, 2.718281828. It looks like it's repeating, but that's just because of the limit of the screen of your calculator. If we were to keep going, those numbers would end up changing. This particular base e turns out to have a slope of 1 at x equals 0. So therefore, if the function we're differentiating is e to the power of x, when I differentiate it, well, I've just said that that slope, that constant we were putting out the front, will be 1. So the derivative is also e to the power of x. So what that means then, if you've got this base e exponential function, then the slope of the curve will always be the same as the height of the curve above the x-axis. It'll always be the y value. So another way of writing that is, in fact, the derivative with respect to x turns out to be the y value. So it's quite an interesting curve. All right, so some examples. If you have to find e cubed, well, you go to your calculator, of course, and e is on the natural log button. So you go shift and then 3, and hopefully end up with something like 20.086. Let's draw 5 minus e to the minus x. Okay, so our basic curve, e to the power of x, I'm going to reflect it in the y-axis, because it's function negative x. So all right, we're now there. Then I'm going to reflect it in the x-axis, because now I've got negative function x. So now I'm down there, and then finally, shift it up 5. And so there's our curve. So 11A, 11B, I printed off a couple of pages of the graphs there, because there's one of the questions says, I'll photocopy this page and do that. So that might be a bit easier if I printed one off for you to use.